Okay, this next section is going to be reasonably mathematical. There's not much I can do about that, but hopefully the bits we've done so far will at least prepare you for that. And there's also the full derivation with kind of explaining steps included online. So after this lecture, or at some point before the next lecture, please take the time to go through and work through that. Make sure you understand it. Any questions you've got, please let me know. So the process now is we're going to solve exactly the same equation you've solved, which we now know the solution is just a straight line, using the finite element method. So we've got a nice advantage that the end result we're going to get is essentially a straight line. But hopefully by doing this, you'll get an idea of how the process works. So just to give you a kind of bit of idea of the kind of typical terminology you normally see in the literature, if you look, they'll have the kind of equation in the form AU minus F. So it's an A rather than a K that we used before. But essentially, this equation you can see is of that form. If A is d2 by dx squared, U is t, and F is equal to 0. So typically a general solution of some equation of the form AU minus F, this is kind of a special case of that. So every equation we solve will be of the form AU minus F, and I'll keep coming back to that. But for the purpose of today, essentially, when you see A, you can just replace it in your head by this d2 dx squared operator, and an F is just set to 0. Okay, so the process is exactly what we've seen before. We're approximating the solution of that function with a series of straight lines, if you like, a series of elements. Now, this is potentially a bit misleading because we already know the solution is a straight line, but here it's just a kind of general function, u of x, and this method again is kind of general. So the process here is essentially we're going to minimize the error in this solution. So the solution AU of the elements minus f is approximately equal to 0. So this solution is only an approximation. And we've already seen by putting in that value of 0.5 how poor an approximation is sometimes can be. And obviously we endeavour to kind of make the elements finer and finer. This brings in the idea of resolution that we'll come back to and talk about when we start talking about more applied and kind of industrially focused kind of examples. But the key point here is that this is essentially an approximation. And what we're trying to do is we're trying to use a kind of least squares fit to get the smallest possible error. Now least squares, I think from the survey most people are at least broadly familiar with it. Let me just get this full screen. Your process is one of, you've got a series of points in principle and you want to fit the line that fits those best. So you're actually minimizing the error between each of those points and the line you're fitting in a kind of least squares sense. So you're kind of summing up some weighting, I, which you can make arbitrarily small, times the difference, the error in those values. In a kind of least square sense, and this is exactly this process. We have some weighting function, this approximation that we know is approximately equal to 0, and we're trying to minimize basically how well our solution, our fit to that function describes that. So that's essentially the process of the finite element methodology, and then everything else from that point on is algebra. And this is the weighted residual form, and I'll talk a bit more about the other forms. Okay, so this process now is essentially to solve the integrate of a weighting function times this differential equation integrated over the volume. And this volume is the entire domain, is equal to 0. So it's essentially the same solution we've just seen, but what we're doing is we're solving it in what's called weak form. So the steps we're going to use mathematically is we're going to use integration by parts to make this expression easier to solve. Now, if you go to any textbook, this is typically the methodology they use. You can try to do it directly, but essentially for this problem, it makes it easier, and it has nice advantages in terms of the link between the various elements. What we're then going to do is replace the weighting function, W, and the expression T with those linear approximations we've derived. So you've already seen the U of the individual elements as N1 and N2, and we're essentially going to go through and stick those in to get a linear approximation of our function. And then essentially we're going to collect together these simultaneous equations, which are essentially describing a series of lines that are approximating our function, and then solve an overall matrix for essentially a set of simultaneous equations for the entire system. So that's essentially the process. And what I'm going to do is I'm going to work through and show you how that's done in practice. So hopefully intuitively at least you've got an idea of how that works. Sorry, one second. Okay, so the process here is we're going to basically solve integral of w d2t by dx squared dx is equal to 0. And the whole point of this is we're going to do it for one single element. So you imagine your kind of general function, and then you're solving, say, for a given element, and this is between, say, x1 and x2. So we're essentially going to write an equation for this single element function. We're going to collect it with the element function for all of the other different bits and pieces into a matrix and solve a series of simultaneous equations that give us the overall solution. So the integral limits in this case are between x1 and x2. Okay, so if you remember the steps I mentioned, first of all, we're writing this in what's called weak formulation. This is essentially like a weighted residual, a minimal least squares solution. And we're going to rewrite this using integration by parts to make it a simpler form. Now, the advantage of doing this, integration by parts, is we actually get two first-order derivatives rather than a second-order derivative, which makes it easier to solve. It also has a nice advantage that the link between the two elements is essentially automatically satisfied, as I'll show you later on. So the first thing to do is to replace this using parts. Now, hopefully most of you remember how to do parts. If you don't, the easiest way to derive the equation for integration by parts, if you have, say, two functions, u and v, is the derivative of that you can just write as u dv plus v du. Then you just integrate both sides. And so the integral of the derivative essentially just gives you uv. And what we end up with is this expression. And then we can rearrange it. So we get u dv integrated is equal to u v minus v du, like that. So it's just a way of essentially rewriting the equation in terms of parts. Does that make sense? Where in our particular case, we're going to choose dv is going to be equal to d2t by dx squared. Our u is just going to be equal to w. So this is just taking from this equation up here. And then essentially all we do is we differentiate du to get dw by dx, and we integrate v, which just gives us dt by dx. So essentially just integration by parts. Anyone never seen this before? Completely horrified. Okay, good. So what we end up writing is essentially the integral, and you can see if we put w in there, w d2t by dx squared dx, which is our first expression, is then equal to, and bear in mind between the limits x1 and x2, we now have the u and v term, so that's just w and dt dx, like that, where the limits are between x1 and x2. And then we have our minus v du term, where this is just the integral of the v term, which is dt dx. And we have our du term here, which is dw dx. So this is purely just algebraic manipulation to get it into a slightly easier form. Now, in terms of the physical interpretation of this, you can think of this as essentially a way of writing something as the expression for the surface term. So this is the surface term, and this is an internal term. Now this is in one dimensions. Sorry about my writing. So before, when we looked at this, you can see the surface term are where they join, essentially the interface between the two. And what we have is an expression for the flux at that surface, and then the internal terms are the one inside the element. More generally, as we move to kind of higher dimensions in 2 and 3 dimensions, physically what you can think of is this is like this expression is the internal term. Let's call this I circle, and this S circle. You can think the internal term is basically the mathematical expression for what's happening inside, and then the surface term are basically what flows over the surface. So intuitively you can think of this as kind of rewriting in terms of the two contributions of this equation, if you like. Okay, so first of all we're going to try and approximate our internal term. So the next step is to use linear, so these are the element expressions in equation. So we're going to start by putting them into the internal term here. So the internal term, you can see, is of the form, leave the minus sign out for now, is of the form dt dx, dw dx, dx. So what we're going to use is our element expressions of these two. Now we've already seen that t for an element is equal to n1 t1 plus n2 t2. So this is just our equation for a straight line that we've derived a few times. We do exactly the same trick for w. We're just going to replace that w, that weighting function for the kind of least squares process, with exactly the same linear approximation. Now this isn't the only thing you can do. There are other options that will give you different orders of approximation for your finite element methodology, but this just happens to be the simplest one. So we're essentially just approximating our two expressions. Now, as we saw before, doing dt e by dx is just equal to t1 over, sorry, it's t1 over h plus t2 over h. Whereas you remember before, dn1 by dx is just minus 1 over h, and dn2 by dx is 1 over h. So this is just a consequence of using linear shape functions. The gradients of those are just 1 over h. And similarly, we did the same expression for the weighting function. D-weighting by dx is equal to 1 over weighting over h plus weighting 2 over h. Okay, so I'm aware I've just shown you lots and lots of mathematics. You're probably thinking this has just escalated quite quickly, but just understand the key steps here. The first one is write a kind of weakened expression for the equations of motion that is kind of a least squares solution. The second step is just integration by parts. Mathematically, all we're doing is manipulating it to put it into a term that's easier to solve. And then all we've done here for this particular part is basically substitute in basically shape functions into there that we've already seen. So we're just substituting in these approximations that we've derived. And bear in mind, these aren't the only shape functions. You could put in higher order or different shape functions, but for now, that's what we're doing. Okay. Let's consider the surface terms next. The surface terms basically are just dt by dx omega, and we're just going to put in limits x1 and x2. So you can think of that as basically just giving us w2 at dt by dx at x2 minus w1 dt by dx at x1. So all this is saying is that we're taking the dt by dx value at x2 and the dt by dx value at x1. So we're just substituting in the limits into this function to get an expression for the fluxes at those points. So you can think of this essentially as giving us, if you like, for this expression here, dt by dx here would be dt by dx at x3, if you like, and the weighting function at x3. So it's just saying we're going to take those values at those points that are the intersection of the two finite elements. Okay, so now the aim is to basically rewrite our initial expression, which is which we said was equal to the surface term plus the internal term, and we're just going to basically substitute in the two expressions we've derived. So that's dw. Just for simplicity of notation, I'm just going to call these boundary b1 and b2, just to save writing them out. But essentially we have plus the internal term here, which we had from above, which was essentially approximated using these two expressions. So that's the integral of t2 minus t1 over h times the integral of w2 minus w1 over h dx. So we just substituted in our expressions here. This is just dt epsilon by dx, and this is tw by dx. Okay, so one thing to note about this equation here is that there's no x dependence. Because we've taken the derivatives, because we've used just a linear approximation, essentially there is no x appearing anywhere in here, which means this derivative we can actually evaluate very trivially as just the integral between x1 and x2 dx is equal to x2 minus x1, which is just equal to h. So this entire integral just becomes h, and what we end up with is an expression where we have h squared underneath, is cancelled with h on top. So let me just write that out explicitly. So we have h over h squared t2 minus t1 w2 minus w1. So we've essentially now got an approximation for our derivative as the value at various points and the surface terms. Does that make sense? Any questions on that? I appreciate it's quite a lot, and we're going to cover this again next week. So this is kind of the heart of doing the finite element process. So there's various elements to this. One is the kind of understanding of the methodology and why we're doing this, which is the kind of use of linear functions, approximating and re-expressing things. And then there's the kind of algebraic part where we're kind of manipulating these forms. So we'll come back and we'll do a slightly more complicated example next week where you'll see the same process again, the same steps, where the algebra is just slightly more complicated. So the next step is basically we want to form simultaneous equations for the elements, for nodes. So essentially what we do is we collect together the terms in W2 and W1. So all we're doing is we're collecting together the expressions for, let's start with W1 brackets. So we're going to start with minus B1 from there, plus T2 minus T1 over H. So I've made a mistake here, this should be minus here, because the original expression for internal energy was a minus here. So that minus there should be a minus here. So that's a minus there. So we end up with an expression which is minus here. So this is minus times a minus, which gives us this over H. Plus the expression for W2, which is W2 times B2, which is this here. And then this becomes T2 minus T1 over H is equal to 0. Yes. So okay, sorry. So essentially what we've done is we've basically just collected together terms in W1 and W2 from this expression. We've got a W1 here. So let me just show you. W2 terms are this one and these ones. And W1 terms are these ones and these ones. So we're just collecting them together. Okay, so what these essentially tell us is that this equation, and this is equal, or an approximation for the original equation, which is the one we're trying to solve in order to get a finite element solution for our system, is satisfied when both of these terms are equal to 0. Now W1 and W2 are arbitrary weighting functions. They're constants, which means essentially we know they're not going to be equal to 0, or we can choose them not to be equal to 0 for the purpose of solving this equation. So essentially what we need is that both term in this term under W1 and term 2 are equal to 0 individually. And provided both of those terms are equal to 0, then the overall expression must be equal to 0. So we're just saying if 1 times W1 plus W2 times 2 is equal to 0, one solution of that is that's equal to 0 and that's equal to 0. So essentially now what we have is two simultaneous equations, and we can rewrite them as two simultaneous equations, where we have essentially T2 minus T1 over H minus B1 is equal to 0. So this is our first equation. And we have minus T2 minus T1 over H plus B2 is equal to 0. So we essentially have two simultaneous equations now. Now the reason for doing this is exactly the same reason we talked about simultaneous equations earlier on. What we're trying to do is we're building up simultaneous equation for each of the different nodes so that we can collect them together in a matrix, solve them for the entire system that gives us an overall global solution that satisfies the equations. So we're going to use exactly the same trick we did before, where we're going to collect these together as a matrix. So we want a matrix of the form where we have T1, T2 here, and that's going to be equal to essentially our right hand side. So you can see for equation 1, essentially the T2 term is one second. I just want to make sure to note, so there's various conventions. You can essentially have these plus and minus. Sorry, I made a mistake. I just want to make sure the convention is the same as the notes. Yes, okay, so essentially what we're going to do is 1 over h here. No, sorry, minus 1 over h here and 1 over h. So we're actually going to multiply this top equation by minus, and multiply this equation by plus. The reason for doing that is just so it's the same convention as the notes. It doesn't make any difference. You can work through in either way, but as long as you're consistent between the two. But I just want to make sure it's the same as the notes, so when you come to that, you're not confused. But essentially, you end up with a matrix of this form. Yes, perfect. And that's going to be equal to B1 and minus B2. So put two equations in matrix. Okay, so these are two equations that are basically simultaneous equations for the two end of an element. T1 and T2. Now if we did exactly the same process have we done the same process for T2 and T3, and we work through the mathematics, what you'll find is actually you end up with exactly the same process. Because there's no difference here. There's nothing we've assumed that's unique to a particular element. It's a general equation for any element. So actually we'd work through. So if this is element 1, and this is element 2, for element 2, the equation would be of the form 1 over h minus 1 over h, T2, T3, and that's going to be equal to B2 and minus B3 like that. And similarly for element 3 and 4 and 5 and so on. So essentially the process is general and would work for any element. And essentially these 1 and 2 are just arbitrary coefficients. So then what we start to do is we start to collect together the equations. Now the one thing I wanted to, so when we did the three component simultaneous equation with x, y and z, if the component z was missing, then we just fill that in with zeros. So if you think about the equation just for this expression, but we include T1. So you can essentially think the equation for T1 as just being a series of zeros. And then essentially what we have is the expression for so if we write so this is exactly the same example we saw before. We solved three simultaneous equations. In this case, the third simultaneous equation for T1, if we multiply each of these expressions, will always give 0. Essentially, it's a trivial equation. So what this allows us to do is basically to assemble a set of equations. And Let me just write out the expression again. Yes. Okay, so hopefully you can see at least the elements we've written before when it was a 2 by 2 are obviously enough to solve the system of equations, but we can just pad out our expressions just adding some zeros at the end, and then it becomes an equation for as many components as we want. We can include T3, T4, T5. And these zeros make absolutely no difference. It's essentially having an extra simultaneous equation where everything is set to 0. But what this allows us to do then is to add this expression for 1 and 2 together. So we can form a kind of global matrix where we add 2 and 1 together here. And what that gives us is a kind of global matrix where we add, the first term is 1 over h, 1 over h, 1 over h from this term. Now the middle term we're adding between the two. So this term is added to this term here. And we end up with an expression that's minus 2 over h. We still have a 0 here because we have 0 here and here added together. I'll show you that and that. And then we have a 1 over h here. We have a 0 here, 1 over h, and minus 1 over h here. So this is kind of what's normally called assembling together a matrix of global equations. So we've written the expression for the individual element 1 and 2, and then what we're doing now is we're adding together the equations for 1 and 2 just to get a kind of a matrix that's valid for both element 1 and element 2. And so what happens then if we do that on the right hand side is we have b1 plus 0, we have b2 minus b2, and we have minus b3. So what you can see here is the right hand side, this term has essentially become equal to 0. And this is essentially why that concept of having the surface term makes sense. So when we talked before about having the kind of element between two nodes, where we said this was say b2, you can see that b2 for element 1 must be equal to b2 on the left of element 2. So the two cancel each other out, and we actually end up with these kind of surface terms cancelling out between the two elements. So that's just a statement that the two elements essentially are connected together as part of our global solution. Okay, so if you go through the notes, we do this for 4 elements and we work through the entire process far more rigorously than I have done here. But the last thing I want to show you really is just basically how we'd aim to solve this. So typically what you do is you'd specify the boundary conditions. Now, specifying these type of fixed boundary conditions can be a little bit tricky, but essentially what you end up doing is eliminating rows in the matrix in order to get the boundary conditions, and then you just invert the matrix in order to get the solution. So actually I think probably better just to stop there rather than trying to go through that, but essentially you can see hopefully that this matrix is of that form. So what we've done is essentially built up a matrix from these various terms, assembled them together, and now we have something that essentially we can solve. Yes. So any questions on that? Have I completely confused you, or it's okay? I think essentially what I've tried to do is kind of give you a step-by-step overview of the main parts of this. I think you're going to have to go away and look at the notes and kind of work through mathematically and just convince yourself of what's happening with this process. Large elements of this are just algebra, so the kind of key steps, if we go back, let me just recap here. So the key steps, essentially we use integration to essentially approximate that second derivative and split it into a surface term and then 2 first order terms. We then substitute in t and w by those linear approximations. And because we have essentially derivatives of both w and t, we end up substituting in their derivatives for them. So essentially what we have is a series of simultaneous equations. So we collect together the terms for w1 and w2, which give us two simultaneous equations that are equations for each of the nodes, and then we form them together and we solve them as a matrix. So we've only done it here for 3 elements, the notes do it for 4 elements, but in principle this process could be used for any number of elements. You can build up a system with an arbitrary number of elements and essentially solve those equations. So that's the premise. Does anyone have any questions on that? Okay, how are we doing for time? So we've probably got about another 5 minutes. I was going to just show you, just for the end as a kind of framing context, and again I'll kind of keep going over this over the various lectures, but essentially this entire process of what you've seen was getting the equations in a matrix that we can solve. So K is what's called the element stiffness matrix. So you can see here K is a matrix we've just formed. U are the displacements. In that case we've just seen there were temperatures, but as we said they could be considered as the shear in a solid substance or the shear in a fluid, deformation of the material. So they're generally called displacements because finite element analysis is more often used for solid mechanics and was derived from solid mechanics. And then this right hand side, these force terms, in our case have been 0. So I just want to kind of give you a quick overview of the various forms of the finite element method that you will see in the literature. And we've seen the weighted residual, which was kind of principle of least squares here. And again, just bear in mind the equations going in are of the form AU minus F, where A in our case was d2u by dx squared, F was some force term. We worked through all of that algebra to get something that's a matrix equation that can be solved in, say, MATLAB, which is K, a big element of the kind of stiffness elements, U the displacements, and F the forces. So it's this process of converting a differential equation into a kind of piecewise solution, collecting together the matrix, and then trying to solve that. So just to kind of give you a brief overview of the other forms you'll see in the literature and a kind of slightly wider interpretation of this. This form of what's called weighted residual is essentially the same as what D'Alembert's principle. So this is a minimization formulation of the equations of motion. So it's kind of a formulation of mechanics in the same way Newton's law is kind of just postulated. No one's proved Newton's law to you. There's no reason why it should be true. No one could actually necessarily show you why it's true, it's just true. In the same way, D'Alembert's principle is the same thing. It's this idea you apply a kind of arbitrary virtual work to some system, and then that kind of small virtual work that you apply gives you a series of equations. But you can see this form of equation is identical to the one we've just done with the weighted residual. So this kind of least squares process is essentially what nature does. Nature, it uses the minimum energy possible. And you can see this in kind of hanging chains, which form a certain shape. So D'Alembert's principle is this statement that essentially the difference or the system will tend to the kind of a particular state using this kind of small virtual work. But this process again will give you the kind of displacement element matrix and forces in the same form. You've seen the weighted residual. And you can, one other interpretation of this, and this comes back to the original interpretation of the finite element method. Those of you who took the 3rd year course, this was the interpretation you saw there. So if you're thinking these kind of elements are all a bit abstract, talking about abstract mathematical functions, you can just think of these as springs. So these elements, if you like, are just springs connected together. And if you're modelling a bridge or you're designing something using the finite element method, it is just a series of springs joined together with some coefficient matrix. So the process of this is exactly what you've seen before. Essentially, the force is equal to Hooke's law, some coefficient times the displacement. And the displacement for spring 1 is just the U2 minus U1, so it's a difference between the displacement at the two ends. And the displacement on the second node is just force 2 and U1 minus U2. So essentially, it's this process which you must have seen before in kind of vibrational analysis, where you build up a matrix of equations for the spring coefficients, and you solve them. And you can see this is exactly the same form as you get from these equations. So conceptually, if you like, you could think of this as springs. You can also think of those springs as being some solid bits of metal, if you like. And those bits of metal have some area, some elastic coefficient, say Young's modulus, and some length. And if you do that, what you can show is there's actually a formulation in terms of energy I won't go through this. I'll leave this for you to look over. But essentially, the mathematics of this is taking this element that you've seen, rewriting it in matrix form, where 1 over h, which you've seen already, is basically the length of the element, which we get from these kind of element functions that we've seen, where the derivative is the strain. And if you work through the energy analysis, what you can show is that you get exactly the same form in terms of springs that I've just shown you. So all of these forms are exactly consistent. So when you come to the literature and you see various expressions for springs and masses, for energy, strength, stress strain energy, or minimization principle, you can show that they are all related. And if you can bother to work through this, this is just the kind of essentially a process of strain energy is equal to stress times strain, and just substituting in the expressions for stress times strain, and then just essentially cancelling coefficients, and you end up with the equation in terms of spring constants, if you like, where these spring constants are just the area times the material coefficient over h, and actually the equation you end up with is just 1 over h. Yes. So yeah, just to make it clear, if you do go to literature and you kind of want to understand the link between all these various forms, they are essentially just different descriptions of the way reality changes, whether it's force equals mass times acceleration, or that energy is conserved, or that we have some minimization principle. And if you go into physics, there's actually a lot of quantum mechanics is actually based on this principle of least action. So it's a kind of more fundamental principle if you start to look into that. But essentially this idea that nature does, that minimizes the difference between potential and kinetic energy. Yeah, so that's it today. That's everything I wanted to cover. Any questions at all? I'm basically here from 4 till 5 in 105, so feel free to stop by, or I think probably get 5 minutes before someone kicks us out, but I'll be here if you have questions. Thank you.